Student, welcome to this lecture on quantum computing for everyone. So I'm preparing this some lecture on quantum computing for everyone for people, but then this lecture quantum computing for everyone is for general audience, like means anyone who want to or interested to understand what is quantum computing, what is this new hype is about, which is coming up. Currently, you are in a AI hype era or AI. Everyone is talking AI. So the new what is a quantum computing and what is this coming up in the future and where is a quantum computing and what is a general information that if you have a general curiosity to know what is a quantum computing, so this short information lecture is prepared for general audience for everyone if you just want to know what this big beast coming up in the future. So let's begin. So my name is Prof. Dilip K. Prasad, and I'm a professor at UIT, the Arctic University of Norway, and I'm also preparing the Quantum Innovation Center at the UIT, the Arctic University of Norway. Now, the in this lecture, we're talking about uh, what is the present classical computer, the classical bits, and where the future, uh, the global quantum race is moving towards. So let's begin. Now, why you should learn about it means why you should care about it. The quantum computing, why? The because of quantum computing, we will be able to discover better drugs. We will be able to use in medicine technology can find better battery materials which can store the battery energy properly and better way and discover better materials for many other purposes. We can have better security system in the future encryption system is going to be better. Currently AI is using classical system. If we can link it with the quantum and we make a commercially useful quantum AI system, then we can have a future hybrid models which has a quantum AI as well as a classical AI, and and they can work together in tandem. And we can also use in the finance sector and like financial modeling and optimizing even for the country financial modeling and other thing we can do the thing. And for simulating the climate, we may be able to predict many months ahead. If we can have a proper quantum system about the climate, we can simulate much better way and then do the predictions. So what is needed in the present time is that means one thing you should take it forward is that we do not need to build quantum computers to understand uh, why they need for the society in how way it will affect the society. We need to build the quantum computers for better use of quantum systems in the suitable environment where quantums are useful. Now, classical computing begins with simple phenomena that if any of you don't know that computer understand in terms of 0 and 1 means like I'm speaking to you and my voice is getting to you via the YouTube. First, anything it is getting recorded, it is getting recorded in a format, and finally in the computer it is getting stored in a format 0 and 1. And this 0 and 1 data, what you call MP3 file or MP4 file, a video file, which is I'm uploading to the YouTube, that YouTube is storing into his own server. And later on, in the YouTube server, it is being stored in 0 and 1. And later on, when it is you are watching via the YouTube, the data which is getting from the cloud server of the Google system, YouTube system, when it is going there, they're all going in a 0 and 1. So basically, the classical systems are built around 0 and 1. And so a bit is basically a unit of classical information, you can see. And to understand very, it's like a switch button in your home on and off. So that is how we can understand the quantum system. And the 0 and 1, one thing means one switch, 0 and 1. If we think, it's very easy to understand, think like that. But in our chips, computers do billions of operation every second, that 0 and 1 switching, and that's how we get a speed up and computing ability, and wonderfully we get the performance of computers. Now, in computers, as I was explaining you, that my lectures are getting converted into 0 and 1. So let's see with some more examples, like how system is getting converted. So when we type message or speak something, and let's say hello, that hello is going to be converted like HELLO. Now all this character HELLO, each characters are standardized by the standard computer standards into some kind of ASCII characters. So like H has a number called 72. When it goes into the system and get transferred like 72. And finally, if we are storing in a 8-bit format, it will be in the form of 00 and 11 kind of thing. Okay, so as you can see, the 72 is 010001 triple zero in terms of 8-bit format. I like that. O, hello, O, small o, is ASCII number is 111, and that is stored in a bit information like 011011111. So in that way, 8-bit, they are getting converted. Now, if we take the same thing to the image, like you see my image, this image is, if it is represented in a 1024 by 1024 pixel, like 1 megapixel, then each of the pixel will have three color information, R, G, and B, because we are into the RGB world, three color world. So each pixel will have value for R, value for G, and value for B. So 0, and they are represented using 8-bit. That means from 0 to 255 options are there. That means 256 options are there. And depending on what number is there, let's say 100 in the R, 120 in the G, B, let's say 160, it will have a color value. And that's how we can see the image in the form of color. Same if we go into the they are represented using the bit, and same we go for video. Video has image and audio, and the images are represented using 0 to 55, and then the binary bits, finally it is same as multiple images are putting along with the audio information. Then the AI model, if you see the AI model, you can see. So AI models are basically nodes. If you do not know what the AI model is, you can watch my lecture on interpretability in deep learning, and that I have taught, I'm still undergoing. And in that lectures, you can know more about the AI models and how the nodes and neurons are connected. So in the AI model, basically it's the nodes, and nodes are connected with the connection, and those connection has a weight. So and the parameters of the node, so all these parameters, like they are being represented in a matrix format, and then they are represented in a 0 to 1 format. If it is 32-bit representation floating type, then 32 times 00111 kind of bit information will be there. Now, if we are sending any information via the internet, and then information via the internet go in terms of packet, and each packet, the information is passing as, for example, like 48, 65, 60, this way of information passing, those numbers are again getting converted into binary number, that is 011 kind of thing. And similarly, sounds are represented using samples and numbers, and then like your audio file .mp3 files, the waves and frequencies are getting converted into finally into a binary number. So now you know that everything which is happening in our world, where you are using anything on mobile phone or computers or any kind of computing activity, anything digital world is happening via the bit conversion between 0 and 1, and operations are happening on 0 and 1 inside the computers. So let's see how the normal computer really works, means how they compute it. Then only we will be able to differentiate how the quantum computers works. So in normal computer, you have an input, and input can be keyboard if I'm typing something, or noise, or a mouse movement, or image, audio, video, or any kind of sensors are sensing data transferred through the internet. So those are can be in inputs. And then there are processors are there in the computer, which we call it a CPU. And if there are parallel processor, we call it GPUs. Then this CPU is going to perform millions of operation inside the system in every second, millions and billions of operation. Now, then the datas are getting stored into memory register. In so like you have a 256 GB memory. Like many of your phone you are using, you say 64 GB, 128 GB, 256 GB, 512 GB. So those are the memory quantity in your phone has. Similarly, the data are stored in terms of memory in the computer, which are uh, non which does not get erased when the system is off. So there are erasable memory, and these are non-erasable memory. So if we normal or the hard disks, the storage devices have non-erasable memory, they keep the data, and even if the power is not connected, you can still recover the data when you again switch it, connect to your computer or any devices. Then finally, you give it the output in terms of image, sound, uh, any kind of print. So basically, everything we need to convert into 0 and 1 inside the computer, and then the inside the transistors are there. And transistor you can understand like a switch, on and off switch, but then millions, billions of switches are turning on and off, because in the CPUs there are millions of transistors are there, and billions of transistors are working together, and together they are doing 0 and 1 billions of operation at any second of time. And that's how we can see the computation happening, or everything happening seamless. Like our computers are working seamless. In your phone you are running 100 200 apps together, they are working, and that's you still does not find any glitch, and they are working together because of this billions of operation happening inside the your mobile phone chips. So in the phone, how the operations are done, basically they are done like add, subtract, compare. There are logical operation, there are mathematical operation, there are decision operation. So those are there. So basically, any normal computer manipulates bit using the transistors on and off, and that's how it is going to process the data and make the system give you the output. So this is, I told you, the how the normal computer works: input, process, store, and give the output. Now, classical computers, what present day we are using, every computer I'm talking is a classical computers. They are very useful and powerful. But sometime, if depending on the problem which we are working on, the problems start exploding because of the complexity of the problem. Now, the classical computers means the thing on which the internet is operating, the smartphones, the AI models, the banking system, the biological systems, scientific instruments. Now, those are all classical computers, and we have been very happy using the classical computers, and they are working wonderful. Now, uh, and with this classical compute system in the modern time, in last 70, 80 years, we have seen a tremendous growth of civilization and lots of new technology and advancement happening, and which is helping to ease our life. Obviously, some challenges also it bringing. So now in the classical computer, let's say if you have a 8 item to search. So classical brute force way means naive way or brute force way, we call it in a computer world, to search one item between, let's say, 1 to 8 numbers. Then each and every items we have to search, and then about n operation or 8 operation we have to do. If there are n numbers, we have to do n times search and then find out if we have reached the proper number or not. That is a brute force way. Now, up to 8, okay. Now, if you have each of these options has two yes and no, 0 and 1 operation. So there are two operation and there are 10 decision to be made. Now, so that means 2 to the power 10 number of operation need to be done or search need to be done. That is 1000 times. And if it is 2 to the power 20 or 20 decision of yes and no, then 1 million times. And if it is 30, then it becomes 1 billion time. And imagine if it is 100 decision of 0 and 1 we have to do. That is uh, difficult to even count also. Now, here comes the use of uh, when this kind of complexity arises and which expand exponentially, then the classical computers start struggling, or it can take few lifetime years. There are certain kind of problem statements are there in the present classical computer. If they have to compute it or find out the answer, it can take 200 years, 1000 years, 5000 years, and none of us can live usually beyond 100 years. So we need to have the operation to be done within our reasonable amount of time. Um, for some operation, every second we need the result. For other operation, we can wait for 4 5 seconds. But for special operation, we can wait for half an hour, 1 hour. But we definitely do not have our lifetime to wait for 100 years, 200 years, or 1000 years. So for those kind of work, we are looking for a quantum computer world. That means when the possibilities become too large between, and it becomes too complex. Let's say we want to understand the society. Let's say India, 1.4 billion people are there. Now, if you want to understand that by doing one decision in the government and how this is going to affect each and every people of 1.4 billion, so you can understand that every decision which government making, and that decision which going to impact many department of the government. And if that become that many option, if there are 80 department in India, 80 ministries are there, all those 80 ministries are affected by one law, then there are 80 decisions to be made and 1.4 billion people. Even for two operation yes and no, you can understand it is not countable. Now if you have to do for 1.4 billion people, then 1.4 billion into 80 times, you can understand where the math goes. So in that kind of situation, if it comes, if you want to do it, then presently the classical system has a challenge to do within our own lifetime. How we can utilize it? So the inspiration we got from is a nature itself is a quantum world. So if you have studied in your physics, that you know that the quantum physics are there. So in the microscope world, basically if we go we are built with an elements like oxygen, carbon, nitrogen, sulfur, magnesium, zinc, iron. All this we are built, and humans or any living elements are major portion of our built up is a carbon element. Now, when we go inside the element, we go into a molecule and then one atom. And inside the atom, things are in the form of electrons, protons, neutrons, and then it is a quantum world we are talking about. So in the atom world, electrons are there and which are always moving. They are not a fixed condition. And the different examples we can see from the nature is like the chemistry, the bond in the chemistry, that there are hydrogen bond, oxygen bond, the organic bonds are there, and those are the energy transfer between those bonds are happening in the form of very small quanta energy. And photosynthesis also receiving the lights in the form of quanta, and then plants are working in the quantum world. DNA and protein making in our own cell lines, every chemicals are being produced in a very quantum microscopic condition. Magnets also works in a quantum world, and then semiconductor in the modern electronics. So quantum physics basically is not the theory; it is basically how it works, how the nature works. That is what quantum physics is about. So in the classical representation, if you go in the with 0 and 1 formation, and then when the problem start statement start exploding, you can see the start exploding the problem statement, then it becomes too complex. The If there are 2 to the power n condition problem statements are there, then it will start growing exponentially, and then it becomes difficult to simulate. So what in the classical system we do, we try to approximate. And now the approximation, if we get true quantum behavior, and here the what we approximate using our classical system, so we get some kind of error, and that's the reason we are not able to simulate the world properly. And now the in the quantum world, quantum computer can represent the nature much better way, and that's the inspiration that why we should be working. And so the idea is nature itself is quantum. The inspiration is nature itself is quantum, and to understand and harness the usefulness of the nature, if we can work in the quantum world, if computer can think in a quantum, then we will have a bigger opportunity and bigger advancement and bigger help to the society. So quantum computers basically may simulate the quantum nature. Nature itself is a quantum. Quantum computers may be able to simulate the quantum nature a more better way, and it can open more and more new possibilities. So classical bit, if you think it is a form of 0 and 1, but when we go to the quantum world, it becomes the psi is equal to the probability of 0 plus the probability of 1, that is alpha and beta representation. So then the superposition is one concept in the quantum world which actually been used. So you understand this way, the classical bit is 0 and 1, but when we go for a quantum world, we call it a qubit, quantum bit or qubit. uh, is basically a superposition, that when the possibilities of 0 and 1 is there, and quantum representation is psi is equal to alpha of 0 plus beta of 1. That means possibility of 0 and possibility of 1 at any point of time. So there are 50% chance of 0 if we think alpha is 50, and then 50% chance of 1. Then uh, this probability together will add up to 100%, and then we get the measurement. Or so it's quantum is not like it's not a magic, but it is a multiple final answer we are trying to read at one time. So there can be multiple outcome, but then at one time when we are measuring with a quantum world, we can be able to measure it. So so when we are trying to work in the quantum world, qubit in superposition, when we are measuring, we are getting the output in the classical way, 0 and 1. So basically, the repeated measurements are uh, revealed as a probability. So the probability will add up, and finally we are getting the one outcome. So superposition gives quantum computers a very richer condition and richer state, and but the measurements still work, and it will return one outcome even if there are multiple possibilities we are trying to work together. So measurement in the quantum state, when we try to measure a quantum state, it will start getting the classical result like 0 and 1. So quantum, it's like if we give run one time, it gives one result, but by repeating multiple times and the multiple runs, it will going to reveal the probability distribution, and finally the outcome will be there. Now, there are myths for the quantum computers, like the quantum computers try to compute all answer and read the best one. And this is not how the quantum works. It is not trying to um, use a brute force approach to read all answer and trying to give you the best one. So myth in the quantum computing is that all possibilities quantum computers are computing, and then they are simply reading the best outcome from the out of all the classical compute all the computation. But what basically reality is that when we try to measure, it gives the one outcome. So quantum world, the quantum algorithms are giving the all this amazing type of work and amazing possibilities adding to the quantum. So algorithms are designed to shape the probabilities such that when we do the measurement and we get the best measurement and we get the less error, most more noise tolerant. And how it does, there is another concept after the superposition is called interference. So quantum world uses the interference, and it's a secret recipe of the quantum world, and that helps in giving the one outcome and doing the utilizing the quantum world ability. So goal here is not to see the all answer. The goal is to make the useful answer high likely. So in quantum, using the interference, what it is done that it subdue or die down the wrong answer, and it enhances the useful answer. So it's die down the wrong answer by destructive interference, and it enhances the useful answer by the constructive inference. So interference, to understand that way, if you have ever thrown a stone into a pond, then you may see that waves going up. And now if you throw the two stone, you and your friend throw the stone together, and they are going to collide with each other. So when they are destructively colliding, then these waves or in the water will die down fast. But if it is colliding constructively, each place they are getting up, and whenever going down. So in that way, we can have a better wave construction, and that is called constructive interference. So quantum algorithm in this case guide the quantum algorithms. The wrong answer it tried to subdue, and the right answer is tried to enhance. So so that is how the if you are working in a quantum world, so you are developing a quantum algorithm. So good quantum algorithms are going to make the bad answer go down, cancel out, and make the useful answer grow. And that's how the quantum worlds work. So you understood qubits, then you understood superposition, now you understood the interference, and the next concept is called entanglement. So that is a concept of quantum world, that in so quantum systems where the possibilities are there, they are being considered to be interconnected, and together they are giving you the wonderful operation. And when we are measuring, because of their interconnection, we are able to get the outcome much better way. So in order to understand in a better way, let's say there is a Bell state examples are being given, 0 0 plus 1 1 by square root of 2. So these are two qubits, a qubit A and qubit B, and together they share one particular information uh, by their quantum combined state. So now if we measure the pair together, we are always going to get for this Bell state 0 0 or 1 1. We will never going to get 0 1 and 1 0. And this has been done because this is happened because the entanglement does not so basically this special property of quantum ball makes it so special that qubit a alone can have 0 and 1, qubit b alone can have 0 and 1. But when we try to measure them together, the results are interlinked. So their outcomes are interlinked. The separate qubit A and separate qubit B together, they are independent. But then we are trying to measure them at a particular time. They are interconnected, and that's how we are getting. They are correlated, and that's how we are getting the 00 and 11 with a 50% probability of each 00 and 11. So the whole system contains the information not which is not fully described by each part of the bits qubits separately. So it's an amazing thing to and sci-fi movie kind of thing. And let's keep it here that qubits, superposition, interference, and entanglement, and that's how it the quantum computing world works. And then entanglement matters because quantum algorithms uh, will enable to speed up for certain kind of operation, and we can do better communication in the quantum communication world. We can have a better sensing using quantum sensing, and then we will have a system which has with a lower error correction. So uh, how the quantum algorithm works or the pattern of working. So basically, first thing is to prepare the condition, makes the useful starting state of the interconnected qubit system. And then there is a mark phase that encoding the problem information. So let's say in this condition, there are so many combination need to be identified, and it is to find the flip the phase for a good solution. And the algorithm can do it between good and bad, and then that is the marking phase, and then the interfere phase where the to cancel out the wrong path and enhance the useful ones, and then finally do the measurement. So when we do measurement, again it works similar like a classical system. We get 0 and 1, and whenever we do the measure at qubits, and we get the classical result 0 and 1. So many quantum algorithms follow this pattern: prepare, mark phase, interfere, and then measure. So examples where the performance can improve using the quantum computers. So let's say there are this is a problem statement. Uh, there are n number of possibilities are there, and we have to find a targeted item. So there are n number of combination. If you do the classical unstructured search, order of n will be the complexity, but there is a special kind of approach is there called Grover search. If you use that approach, then the complexity comes down to order of square root of n. So in the simple terms, let's say there are millions of checks we needed to do. If it is 1024 by 1024 items are there, and to search one item, we have to do millions of checks if we are using the unstructured approach. But using the Grover search, the same thing can come down to 1000 operation for this kind of problems. So only 1000 iteration, and that is a quantum search. One of the search in the quantum search is a Grover search, and with that, millions of operations can be done in thousands of operations. So we are speeding up uh, some kind of activity and task using the quantum ability, and that's the going to help. Uh, the Grover search can reduce the operation from n to square root of n. And so square root of n, you can understand square root of 4 is 2, square root of 9 is 3, square root of 25 is 5, square root of 81 is 9, and square root of 625 is 25. So like that, This way, you can have a lesser and lesser operation using this ability. The another place where quantum world can help is in the performance can do is something called Shor algorithm, and it has a very wonderful use in the cryptography. So in the Shor algorithm, um, 15 composite numbers, finding the composite numbers of 15. Let's say a number is called 3 and 5. Uh, so 3 cross 5 become 15. Now classical factoring, if the number becomes larger, is going to be harder. But using the Shor algorithm, it can factor this. It can find the factor much efficiently with a very less number of operation. And present day encryption technologies are based on RSA, and those are based on this kind of factors, natural numbers factors. And if Shor algorithms can be computed, used to break the encryption, using the quantum computers, then it can be able to break the many encryption, and that's how the public's response is there. You can see the quantum threats are coming up. Governments are very much interested to, and different organizations are interested to prepare the world for post quantum era, means when the quantum computing becomes commercially viable or practically useful, or practically start doing the things which we think, like major places, much more algorithms start coming up which can utilize the quantum world. We just saw the Grover search and Shor algorithm, which is, if done with the suitable quantum ability, then the encryptions can be broken very fast. And so the national, this NIST, which is a world more reputed society for establishing standards and thing, NIST. So they have also released this post-quantum cryptography standards in 2024, and governments are putting money. So the idea is that the Sol algorithms could break some widely used encryption in the future, not now. So the world is currently preparing to post quantum cryptography time. Now, the in the real world, the where is the presently the quantum worlds are there? How what is the progress, and what is where different companies are there? I take forth some examples of the performance milestone. Like in 2019, Google chip Sycamore, they able to show that random circuit sampling, and they shown the random circuit sampling on a benchmark. uh, and then later on the IBM's Starlink has given the roadmap. So they are targeting 200 logical qubits and 100 million gates by 2029. So they are building that system. And then Google in 2024 came up with Google Below, which has shown much lower error, and error correction ability has been shown on quantum, and some performance progress. And then in another company called Quantinuum, and they have S21 2024 shown that their 56 trapped ion qubits has a very high fidelity in a benchmark problem. So important thing is that the benchmark is advantage is not the same as how broadly the commercial usefulness is there. So it is just the quantum world where it is and where it is moving. So how to interpret this quantum milestone using present day the best GPU chip or most advanced GPU chip called H200 servers. That means 8 H200 chips are there in that server. Now the classical high performance computing accelerator with 141 GB HBM memory and 4.8 terabyte memory bandwidth. This H200 server is best for LLM, large language model inferencing, means doing the use of it, and training and classical simulation. Uh, so now, if we compare with the Google Sycamore, where in terms of S200 server, we see that this Google Sycamore is a nice benchmark, is a very niche, some performance on specially designed algorithms or specially designed simulation task. Quantum world has shown some ability. Then if you take the Google Velo 2024 in terms of S200 server performance, uh, it is showing a reliable milestone with lesser quantum errors and uh, not like a GPU style throughput. Now, the IBM is targeting 200 logical qubits and 100 million quantum gates by 29. So this can build a fault-tolerant computing quantum computers and can not by 2029 also it will not replace the classical computers or classical servers. And now if you think with the continuum, this H21 2024, where they have shown 56 trapped ion qubits and high fidelity benchmark. So they have shown very less errors of their quantum technology called trapped ions. And it shows high quality quantum operation is possible and on a certain kind of HPC task, standard task. So S200 server currently dominate today, and quantum milestone is not that it is going to replace the classical wall, but it do show that uh, for some special task, quantum system has advantage, and it will be going to be coming up. So it will work in parallel in a hybrid way with the classical system in the future. So where the quantum computing can help is in the chemistry, finding out the simulating the reactions in the bond level, finding the drug discovery, identifying better materials, better cybersecurity system, doing a better optimization search, and then coming up with early hybrid models which has a quantum AI as well as a classical AI together working together. In chemistry, because medicines or molecules are basically quantum systems, so and classical simulation, it becomes hard to simulate the complex molecules. Now, quantum computers may be able to overcome this classical system inability to simulate the nature properly. So we will be able to do a better drug discovery and catalyst for chemical reaction. It will be good for fertilizers and protein ligand interaction. Now, application wise, it will have application for better battery technology, better solar cell which can store more energy. Means currently, if the sun rays come, the solar even the most efficient solar cell can only convert out of 100 energy or quanta falling into the solar cell, only 30% it is able to store as energy. In future, we may have a better solar cell which can store more energy from the sun. Superconductor system, then we will be able to do the design the some type of materials which can capture the carbon from the society. Now, if you want to know how the quantum computing ecosystem, the full stack, so this is a point of importance to you that there are enabling technologies are coming up in terms of cryogenics, in terms of lasers, chips, and uh, control electronics. So those are enabling technology for building the quantum systems, quantum computers. And then the hardware, some people are developing. Some are going to the pathway of superconducting. Some are going to the pathway of trapped ions like quantinuum. Some are working towards the photonic base, and some are working towards the neutral atom technology. And then on top, these quantum systems are getting connected with a cloud platform so that me and you and everyone can connect it via the cloud to the quantum system or quantum simulators and can work. And then the software algorithms which we are going to use to work for like currently we use Python. So in the quantum world, the new kind of technology coming up and new softwares are coming up like QSkit by the IBM, penny lane, ticket, and then on using that, we are building the application on top of it. So in the quantum computer, there are many people are working and who is building quantum computers. Some example I give you. Using the superconducting technology, IBM is working, Google, Rignity, and IQM, European Superconducting. Then the continuum and ion cubes are working using a trapped ion technology. Then the Pascal and Q era is working using the neutral atoms. And then there are Psi Quantum and Zandu are using photonic based approach to build the quantum system. And then some are using quantum annealing technology like D-Wave, using quantum annealing, solving the problem, finding the lowest energy state. Trapped ion, they are using electrically charged atom trapped and controlling with the lasers, and working. Superconducting, they are taking the conducting almost to the near absolute zero, like in minus of sub 273 Kelvin state. Neutral atoms, they are using neutral atoms to in a different kind of phase with the lasers. So those are the different types of technology people are using to build the quantum computers, and there is a lot to go. There is no single winning hardware yet. I won't be able to say that which is the best one on who is going to win the quantum race. Is it a quantum superconducting or trapped ions or a neutral atoms or photonic or quantum annealing or platform? But there are people are building a platform as well. Like IBM is working, tying up with academia. Google is tying up with academia. So many Microsoft is tying up with academia, and they are building up. Now there are hardware categories, as I was mentioning that superconducting. They are building superconducting chips and circuits. The trapped atom, they are utilizing atoms and lasers and high fidelity system. They are building up. Then photonic based, they are building up those light based technology. And the neutral atoms, they are using lasers, tweezers, and large arrays, and trying to provide promising simulation. And some are working with spin qubits, and some are working with topological and then quantum annealing. So no single hardware currently has win the race. Many people are working. People are parallelly building the platform, and depending on the technology they are working, we will have the trade-off between speed, fidelity, and then scalability, and then engineering complexity. The these companies like IBM, AWS, Amazon, and Microsoft D-Wave are providing their quantum platforms and simulators using their IBM Quantum Platform, Amazon Bracket, Microsoft Azure Quantum, and D-Wave Leap. The software tools and technique they are developing is called QSkit by the IBM, Circ, Penny Lane, Ticket, and Ocean SDK, quantum chemistry optimization package, like that. Now the market and in the investment trends are also there. There are 12.6 billion investment done last year, and 90% of went to the quantum hardware development technology. So many companies are, in reality, many companies are in a very early stage. Investment world or venture capital world is gaga about finding the next AI, which is going to the next hype. So they are putting money on the quantum world. Commercial usefulness emerging is not yet no winner. There are talent that are there, very few talents who knows the quantum algorithm building or quantum technology world. Lots of patents are getting filed, hardware built up, and many government are coming up with the national strategies. So we are trying to get a better future with a better secure system, science, and workforce, and to maintain our sovereignty about the. And many governments are trying to, we know that anything in the present time is getting weaponized. So the talents are also will be weaponized. Technologies are getting weaponized. So they are trying to control this technology also and maintain their sovereignty. So where the governments are funding currently, the European Union are thinking to put 1 billion euro on this quantum technological world as a research funding. Globally, the US, Europe, China, UK, Canada, Japan, Australia, and Singapore are building national quantum strategies. Just like AI strategy, they are also building up quantum strategies. So race is about computing, communication, sensing, security, and workforce. We talk all lot about quantum. So there are lots of myths are there and lots of related to quantum computing. So let's go one by one, some myths and reality. The myth is that the quantum is fast for everything, but reality is that we saw that it is only useful for certain special problem classes like a global search or algorithms. Myth is that it will replace all the my laptop, everything will be quantum, but it is not. Uh, the quantum will works with the classical computers, and uh, myth is also that quantum reads all answer and it gives the best possible answer, but it is not. Measurement gives one result, and algorithms enhances the probability of best result or the most accurate results. Myth is that the quantum has already break the encryption. Our 128 bit to 56-bit are broken, but currently it is not. A fault tolerant able quantum system is needed, which is not yet available. Another myth is that more the qubit of a system, better is the quantum technology, but actually it's not about the how many qubits. It's more about the quality or fidelity or logical qubit is matters. And another myth is that quantum AI is going to replace the modern AI, the GPU based systems. Quantum machine learning is still in a very early stage. It will have take a long way to go. But yes, it is emerging. Quantum computers are special purpose tools. It will be used as a special purpose tools. It is a not a magical replacement of present day classical computers. So, final takeaway for us to in this class lecture is that quantum computing is a new model of computing, and classical computers works in a 0 and 1, and while quantum computers works in qubits using superposition, phase, interference, and entanglement. They are not magic, not faster for everything. They are good for some special tasks. They may transform chemistry, materials, cybersecurity, and scientific simulation. And global ecosystem in the quantum world is basically the hardware, software, and cloud platforms. There are many startups are working on it, governments are working, and the university has a lot of bigger role to play. Like the Quantum Innovation Center in the UIT will also have a role to play, and like that, many other universities are working towards it. So the content here been given shared to you based on this fact from this Google Quantum AI, IBM Quantum blog, and then quantum press releases by S2, one Continuum, and D-Wave documents, McKinsey Quantum Technology Monitor, European Commission reports that in 10 years how much money they are going to put, and NASD post-quantum cryptography project and 2024 principal secrecy standards. So with this, I'll say that I hope you understood bits and pieces of quantum computing and generally where the quantum world and what are the different companies are working, different technologies, where quantum can help, and what are the myths and what is the reality of quantum computing. I hope you enjoyed this lecture, and hope if you like, so then do like my lecture videos and comment and subscribe, share with your friends, and then see you again with the next lectures. Thank you.